Thanks to the organizers for putting together such a wonderful conference. So this talk is on the joint work with Charles Pfefferment. So I will speak about the two problems that at first sight do not seem to have anything to do with each other, but yet the solutions of one leads to the solution of the others. And what is more interesting is that one problem is in analysis and the other is in algebras. So I hope that I will entertain to both the analysts and the algebraists in the audience. Okay, so to state the problems, I need to fix some background notations. So as before, for today, or for this talk here, the integers, we will fix the integers d, n, and m throughout the talk. So the notation Cm on Rn with value in Rd denotes a vector of d tuples of Cm functions, and we equip it with a norm. Cm on Rn with value in Rd is the sup over all x, and for derivatives up to order m for each of the component functions. Okay, so, and we will be working with another subspace of Cm, namely Cm omega of Cm, consists of functions on Rn with value in Rd, for which the Cm omega norm is finite. So the Cm omega norm is defined to be the max between the Cm norm and the sup for the divided difference of the highest derivative. So the ratio to here is the omega functions is going to satisfy the following conditions. It's called a modulus of continuity. So it's defined on a unit interval such that omega 0 is 0, omega at 1 is 1, is an increasing function, and the ratio between omega and the identity function is decreasing. So as an example, so throughout this talk without loss of generality, you can think of omega as just the identities. So in this case, Cm omega is just Cm1 on Rn with value in Rd, consists of functions whose highest derivative are Lipschitz continuous. So without loss of generalities, you can just think of the Cm omega as Cm1 here. And so script m, script p's, mn to the power d will denote d tupled of degree m polynomials in n variables. And mjet for a function, a real valued function, is just its mth degree Taylor polynomial at the point x. So it's written explicitly here by this formula. And then we can also obtain the mjet for a vector valued function, namely is that we're just going to take the mjet for each of its component functions. Okay, so that's the notations. Armed with that, we can state the problems of interest. So the analysis problem asks the following. So suppose we are given the function space Cm, omega or Cm on Rn with value in Rd, and we are given the following data, a subset of Rn, so it's arbitrarily with no good geometry at all. And at each point, we are given d tuples of polynomials, so it's mjet. And then at each point, we are also given a convex symmetric subset of the polynomial space. So symmetric here means that if P is in the convex set here, then so is minus P. So that's what it means for it to be symmetric. So this set here represents the tolerance for errors. So we want to ask whether we can find a function defined on all of Rn in this function space and a constant m such that the difference between the mth jet of the vector valued functions and the given polynomials lies in some dilated version of the sigma. A more concrete version of this problem has been talked about extensively by Charlie. So in a more concrete case, in the scalar case, the following problem, it can be reduced to the previous problems. So sigma is a real valued, a positive non-negative valued function on the set E. It represents the tolerance for error. And so to determine whether there is a function that matches with the given function at the point x up to this error with some universal constant m is equivalent to asking whether there exists functions defined on all of Rn in either Cm omega or Cm, such that the jet differs from the given functions by something in the convex symmetric set sigma, which is defined as follows, is the collections of mth degree polynomials such that at the point x is controlled by this error functions. Okay, so if you, the general problem that I stated in the previous slide, when specialized to this convex set, gives immediately the problems that Charlie has been talking about. So the scalar case is well understood. So in the case where you look at only one derivatives is due to the work of Uni-Bruni and Paul Schwarzschild, and for higher derivatives, it's due to the work of Pfefferment. Okay, so I want to say something about this general problems here. So we are looking at vector valued functions. Let me just issue why it's interesting, or why this should be a 45 minutes talk instead of a 5 minutes talk. So the most obvious ways of doing the problem does not work. That is, if you're trying to solve the problem component by components, there is a problem. So if you do it component by components, so suppose at some point we are given this convex symmetric set sigma is this elongated ellipse. Okay, so if you try to solve the problem by component by component, you only pick up solutions that lives in this small unit squared. Okay, so in other words, we will miss a lot of candidate solutions. So solutions, for example, that lies in here is not included if you do it component by component. So this problem is not immediately trivial. But if you stick around to the end of this talk, then you will see that it's not so difficult. We can trivialize it to the case of the scalar case. Okay, so that's the end of the statement for the analysis problem. So here comes the algebra problems. Is the Brenner-Hoster-Koehler problems, abbreviated as BHK. So let x be Cm omega or Cm. So we are looking at real valued functions. So we are given the following data: a subset, an arbitrary subset of Rn, and real valued functions g1 through gd, and another function gamma on the set E. We want to decide whether the gamma can be written as linear combination of the gi's with the fi's in the function space omega as the coefficients. Okay, so when the f1 through fd exists in this function space capital script x, we say that G is in the X closures of the ideal generated by the collection of functions G1 through GD. So that's just a terminology. So in terms of histories for this problems, Holger Brenners in 2006 studied this problems under some restrictions on the functions, and he was able to show that if you look at the Z0 or continuous closures of the ideals, then you can describe the closures in an algebraic way. That is, without resorting to any analytic properties. And then Hostert in 2010 give lectures on the subject, and Janos Kolar happened to be in the audience, and he picked up the problems, and later on the Pfefferman and Kolar studied the problem and give a full solutions for this problem for C0 of Rn. So today we will be looking at the more general situations of higher derivatives. Okay, so just some trivial remarks regarding these problems. So suppose all of the functions we are given, G1 through GD and the gamma, are polynomials. Okay, and let Z denotes the set of common zeros for the polynomial G1 through GD. Now, if we are going to look for polynomial solutions to these equations here, so we're solving this problem on all of Rn, then this problem of deciding whether gamma lies in the ideal generated by the GI is elegantly solved by using the division algorithm and the Grobelin basis. And moreover, the other trivial situation in which you can write down the solutions quickly is when the collections of common zeros is empty. In that case, you can just define the Fi to be the weighted sums of the gamma. Then you can check immediately the product of that will give you back the gamma. Okay, so if the So that guarantees that the denominator here is not zero. Therefore, it makes sense to divide it. So the interesting case to understand is when the set of common zero is not emptied. Okay. All right. So the two problems, namely the extension problems and the Branner-Hoster-Koller problems, are related. So the relation is given by the following slides. So if you look at the MZ of any solutions to the BHK problems, then it belongs to the following set. So it's the collections of D tuples of polynomials such that at the point x, it solves the linear equations here. Okay? So if the F solves that, so does the jet. So if the set defined here is not empty, then we can pick out a representative element from it. So say x0, p sub x zeroed, and then we can write this set in a different form, that it is this particular representative element plus the sigma of x, which you can think of it as the kernels for this linear equations here at the point x. So it's just a particular solution plus the kernel. Okay, so we have a solutions to the BHK problems if and only if the jets for the functions differs from this particular solutions by something in the kernel. Okay, so therefore, to determine whether there exists such a function that satisfies the latter conditions posted here is a special case of the extension problems. Okay, so that's the connections between the two problems that I stated. Okay, so to look at the extension problem and then the Branner-Hoster-Koller problems for CM omegas, so we want to ask the following questions. For what kind of convex sets sigmas that appears in the statement of the extension problems here, can we solve the extension problems? So this problem, as it states here, is hopelessly general to solve. If we can solve that for any convex set, then it says that you can solve any linear PDEs, and that's too general a statement to be true. Okay, so we can identify a collection of convex sets, which is important in the following sense. So the collection is big enough so that it contains the set of interest. So in particular, it contains the set that arise from the Branner-Hoster-Koller problems, namely this set here. And this collection is not so general to the extent that we cannot say anything. So we can, for this collection, we can solve the extension problems. So when we want to identify the set, we want to keep those two things in mind. So the collection of set we identified are the so-called Winnie omega convex set. So sigma of x in the polynomial space is called Winnie omega convex at the point x with Winnie constant a, if and only if the following conditions hold. So sigma is closed, convex, and symmetric. Again, symmetric means that if p is in sigmas, so it's minus p. And the following ideal-like property holds. Okay, it says that if you pick any element from the sigmas and any polynomials, any degree n polynomials in n variables, fix a delta between 0 and 1, whenever the polynomials p satisfies this inequality here, that is pointwise controlled by omega deltas at the point x is controlled by omega delta times delta to the m minus the numbers of derivatives that you differentiate. And the Q here is to satisfy this inequality here. Then if you take the product of those two things component-wise, then it lies in the dilated version of the sigma. Okay, so the funny product here is defined as you take the product of two polynomials and then truncate terms with degrees m plus 1 or higher. So you look at the product of two polynomials, look at this mz at the point x. That's how we define this product, funny product here. Okay, so this defined for you an ideal. So if you remember one of the lessons in Charlie's talk yesterday for the classical Winnie extension, so it says that basically this is the estimate that you have for the partition functions. So if we have two functions that satisfy the natural growth condition, you ought to be able to take the you ought to be able to take the product and then preserve the product of the thing needs to lie back into the set of interest. Okay, so as an example of such a thing, so if you look at the convex set that arise in the Branner-Hoster polar problems, namely this set here, is Whitney omega convex with Whitney constant 1. It's easy to see because you multiply this thing here by any polynomial Q, it still lies in the same set. Okay? All right. So to answer the extension problems, we have the following theorems that says that fixed integers m, n, and a d, let k sharp to be this number here, 2 to the dimension of the polynomials in m plus 1 of degree m plus 1 in m plus d variables, or more explicitly written in the binomial coefficients like that. So suppose we're given an arbitrary subset of Rn, and then an mjet at each point in the set E, and at each point we are also given a Whitney omega convex set with Whitney constant 8. So this is the given set of data, and we have an assumption. So this is the so-called finiteness conditions. So assume that we can find a finite constant m, such that the following is satisfied for all subsets of E with no more than k sharp points. So the k sharp is defined here. We can find a function defined on all of Rn's in the space Cm omega, such that if you look at the jet of the function, it differs from the given jet by something in a dilated version of the sigma. And then if you look at the Cm omega norm, is controlled by this same constant m. Okay, so under these conditions here, then we are guaranteed a function in Cm omega defined on all of Rn's with value in Rd, such that it satisfies the same conditions here, but for all x in the set E. And moreover, if you want to look at how big its norm is, it's no worse than a universal constant multiples of this m. So universal constant multiple here means that it's allowed to depend on the Whitney constant A, the numbers of derivatives that you look at, and the dimensions for the domain and the dimensions for the target space. Okay, so this is so-called the finiteness principles. I want to say a few things about it. So the theorems effectively reduce the extension problem for a general set E to the special case of finite set with bounded cardinalities. So in other words, we have broken up the general problems into a collection of subproblems, and for these subproblems, we hope that is as it stands, it's probably not too difficult to solve if you're looking at the bounded numbers of set. Okay, so the scalar case of this theorem was already proven by Pfefferman in 2004, and also Uni, Buni, and Pavel Schwarzman for the case where you look at only one derivatives. And also Buni and Schwarzman proved this theorem with the Sharp constant in the scalar case for one derivatives is 3 times 2 to the n minus 1. And so in the scalar case, Pfefferman's original proof produced a bigger constant k sharp that's bigger than is stated here. But later on, Beer-Stone examined the proof more closely and came up with the refined constant 2 to the dimension of the polynomial space. And also Pavel Schwarzman give an independent proof of the same result. Okay, so and I should also mention that Schwarzman has an unpublished proof of this theorem here for one derivatives. Okay. All right. So armed with theorems 1, that is the finiteness principle. So how can we solve the BHK problems? So here is how you decide whether the BHK problem is solvable or not in the function space Cm omega. Okay. So it suffices to know whether the BHK problem is solvable for finite sets with bounded cardinality. That's the consequence of the theorem 1 that says that it suffices to understand the situations for finite set. So how do we understand the problems in finite set? Well, to check the solvabilities on a bounded finite set with k-sharp points, it suffices to look at the following linear algebra problems. So we want to know whether there exists a constant m such that given any k-sharp points, x1 through xk sharp, let's say we are working in the unit cube, And for each point, we attach to it, associate to it d-tupled of polynomials. So it's labeled as such that it satisfies these equations here that was imposed upon us by the Brenner-Holster problems. And moreover, the quadratic expressions here is going to be controlled by the M. Okay, so this conditions here is the Whitney conditions. So if it is bounded, if we can come up with such a constant M, then the classical Whitney extension theorem tells us that we can come up with the Cm omega functions having those functions as its jet. Okay, so therefore, we can once we can produce those polynomials, then we can check the conditions for the for theorem 1, and therefore we can answer the BHK problems. Okay, all right. So so far as we talk about how to solve the BHK problem in the setting of Cm omegas. So what about in Cm? So in CMs, first of all, we don't have a finiteness principle if we are looking for, if we are solving the problems for general sets E. For finite sets, Cm and Cm omegas are the same problems, so it makes no difference. So instead of a finiteness, instead of the finiteness principles, we have a finite procedures called a Glaser refinement. So in the next few slides, I'm going to define for you what a Glaser refinement is. I think we have already seen have a glimpse of the concept. Charlie spelled it out a little bit, although he didn't mention explicitly that it's the Glaser refinement. Okay, so here is some definitions. So a bundled over set E is just a family of affine subspace of the polynomial space indexed by the set E. Okay, so it's in the form of some polynomials, vectors of polynomials, plus some submodules of the polynomial space, so sigmas of x. So each members of this family is called a fibers of the bundled at the point x. And then suppose we give another bundled over the set E, so H prime is a subbundled of H, and we write it as H contains H prime. If the corresponding fibers for the H prime is a subset of the fibers, corresponding fibers for H. Okay, so that has to be true for each x in the set E. So a Cm sections of a bundled is an RD valued functions in Cm on R end, such that its mth jet lies in the fibered H of x for each x in the set E. Okay, so let me give you an example that shows this kind of that illustrates this concept. So in the settings of the BHK problems, we can obtain a bundle as follows. So H of x is just a set of polynomial at the point x satisfy the linear equations here. Okay, so obviously you can write it in the forms of a particular solutions plus the sigmas, which is the kernel. Okay, so the BHK problem is equivalent to asking whether the bundles are formed by grouping together all of this set has a Cm sections. Okay, so how do we answer that? So suppose, okay, so here is the definition of the Glaser refinements. For fixed integers m, n, and a d, and some numbers k sharp that's big, but that is determined entirely by m, n, and a d. So let H be a bundled. The Glaser refinement, denoted as H primed, is a subbundle of H, is defined as follows. So at each point x0, and we pick an element from the fibered at the point x0, so we want to know whether we should put it in the refinement or not. So we can do the following test, that if for any given epsilon greater than 0, we can find a delta greater than 0, such that for any point x1 through xk sharp that lies within an epsilon neighborhood of delta neighborhood of x0 in the set E, we can come up with a corresponding polynomial for each of the points that lies in the corresponding fibers with the following inequality hold. So this is reminiscent of the Whitney conditions. Okay, so this procedure here is to make sure, so to begin with, these collections of fibers, they don't have anything to do with each other. So by doing the Glaser refinement is to making sure that the fibers, they talk to each other. Okay, so in particular, the x0s here is related to the x1 through xk because it satisfies these conditions here. Okay, so so some important property of the Glaser refinements that enable us to answer the BHK problem is the following, that if you look at the Glaser refinement of the given bundled, it's a sub-bundle of the given bundled, okay? And so that's easy to see because each fiber, H prime, is just a subset of the given fibers. Okay, and any sections of a bundle is also a section of its refinement. So that's a consequence of the Taylor's theorem. So this is the relations that it has to be satisfied by the Taylor polynomials of a CM functions. Okay, and moreover, the following is true. So you can play this game. So once you have its refinements, you can take its refinement again. So you can keep doing this, and then the question is, do you keep getting new things? And the answer is no. After finite numbers of steps, the thing you get will stabilize. So we let H sub L plus 1 denote the Glaser refinement of HL. Okay, and if L is bigger than this constant L, which is given by 2 times the dimension of the polynomial space plus 1, then all of the Glaser refinements are the same. Then meaning that it stabilizes only after a finite number of steps, and in fact the numbers of steps is predetermined by the numbers derivative and the dimensions that you are in. Okay, so so what is the upshot of the whole thing? So theorem 2 says the following. Suppose we're given a bundle, and the bundle has the following property that when you take its Glaser refinement, it coincides with itself. Okay, so it's its own Glaser refinement. So if each fibers of the bundle is not empty, then we know that the bundle admits sections. Okay, so that's equivalent. The two conditions here are equivalent. So that means to tell whether a given bundle has sections, we can do the following things. So we know that after finite numbers of Glaser refinements, the bundle will stabilize. So we start with a bundle and then start doing the Glaser refinement, and we stopped when the Glaser refinement stabilized, and we guarantee that we can do that in a finite numbers of steps because of property 3 here. So after the thing stabilized, we then look at the fibers for the for the stable Glaser refinement, and if the Glaser refinement after it's stabilized has non-empty fibers for each fiber is not empty, then we know the original bundle admits a section. Okay, so that's how we tell whether the given bundle admits a section or not. Okay, so as an example, so here is an example taken from the joint work of Pfefferman and Kolat. So it's a problem, is an example given by Hostert. So this example here is interesting in that, so you can try to come up with a list of consistent conditions to check whether you can find the gamma as linear combinations of G1 through G1, G2, and G3. So it turns out that it satisfies all of the list of conditions, but at the same time, you cannot tell that whether it's in the closure or not. Okay, so let X be the points, denote a point in R3. So G1 is the polynomials that you X1 squared, and G2 is X2 squared, and G3 is X1 times X2 times X3 squared, and gamma is X1 times X2 times X3. So the claim is that this gamma here is not in the C0 closures of G1, G2, and G3. Okay. So how do we so how do we look at this in terms of the in terms of theorem 2? All right. So the bundles that we want to look at is the initial bundle is, the initial fiber is defined at each point to be the collections of points in R3 that satisfy the linear equations here. Okay? And when you want to look at its refinement, so it's just the collections of points in the previous fiber such that the distance from the nearby fibers tends to 0 as y goes to 0, tends to x. Okay? Now, so that's the same. Okay, so this set here basically defines for each fixed x, it defines for you a plane. So this is just asking the points, the distance from a point to a plane when it goes to 0 as the point approaches each other. So it's the same as equivalent to these conditions here. So, all right. So the thing is that if you want to look at this refinements for any point x, well, so it has to be, so it's saying that the GIs here has to grow, so it's little o's of the GI, so as y tends to x0. So therefore, the lambda 1 that is attached to the x1 squared has to be zeroed, as if this is to be true. And so is lambda 2 that attached to this to these functions here. Lambda 3, you have a choice. So if you fix an x, you can choose the lambda attached to this function here to eliminate this quantity. So in other words, for any points that's different from 0 in the third component, its Glaser refinement, the first Glaser refinement consists just 1 point here. But on the other hand, if you look at the fiber at the point x0, well, the initial starting point is just all of R3, okay? And the first refinement, it consists of 0, 0, and then the last component is any real variable. But if you look at another refinement of H1, then you see that it's empty because any points that's fixed to this quantity here, it blows up as x3 tends to 0. So according to theorem 2, there's no continuous section of this bundle because this fiber here is emptied. Okay, so that's how we see that the Hoster problem does not have a CM solutions. Okay, so and then the next question is so the Glaser refinement is useful for answering the Brenner-Hoster-Kohler problem. So the next question is how do we actually compute it? So here is, so the definition is more qualitative. This is a more quantitative way of defining the Glaser refinement. Okay, so given the K-sharp point and associated to, and also K-sharp polynomials, so P0 through Pk sharp, and we look at this quadratic expressions here. So it's the sum of all the derivatives up to order m with this divided difference here. Okay, so for each point in a unit cube and for each P0s in the fibers, we want to look at these expressions here. So it's minimizing these quadratic expressions over all polynomials of P1 in the fibers x1 and Pk sharp in the fiber xk sharp. Okay, so given the points in a unit cube and elements in the fibers at the point x0, so we will put that in the refinements if and only if this expressions here tends to 0 as the ball shrink to 0. Okay, so that's a more quantitative way of checking whether something belongs to the Glaser refinements. Okay, so I want to say something about the proofs of the theorems. So in particular, so the idea is to reduce the vector value situation to the scalar situation in which the theorem has already been proven. So I will demonstrate this in the case of theorem 1. So we want to show that there exists this real valued functions defined on Rm plus d with real taking value in R, such that the following holds, that G of, so x hat represent the first n component, and V hat represent the last D component. So if you set the last D component to be zeroed, it's the identically zero functions. And so if you want to look at the jet for this function, for each V, so V for the components corresponds to the V vector, set it to zeroed. Look at its jet for the X, then it has to lie differs from the given polynomial within a constant multiple of the sigma. And then this functions here is, when you look at its norm, is no bigger than constant multiples of the M. And if suppose that we can find such a function G, then we can obtain a solution to the extension problems just by setting F to be the gradient with respect to the last D component at the point x0. Because look at this expression here. That's exactly what we want. And also we have this control here that tells you that it's in the appropriate function space. Okay, so then the question is how to reduce the scalar to the scalar situation. So we need to come up with a set of data to fit into the scalar version of the theorem. Okay, so let me remind you what a theorem is. So this is the theorems that we want to prove, and for D equals to 1, we already know that it's true. So here is how we can reduce it to the case of the known situations. So given an arbitrary subset of Rn and then an MZ and an omega convex set with Winnie constant A, so we are going to define the following data. So E tilde is going to be defined to be E cross zeroed, consists of D tuples of zeroed. And for each point x tilde in the set E tilde, we are going to define an M plus 1 jet. So we're going to upgrade it by one dimension. So at each point here, so it's a function in x hat and a v hat. As a function, it depends on those two parameters or those two independent variables. So we are going to, so this is the given polynomial's degree m. So we are going to multiply by, upgrade its order by 1, by multiply by the Vj component. Okay, and then the convex set of interest is going to be defined to be the collection of polynomials such that when you set the last D component to be 0, is identically zeroed. And also, when you look at its jet, that is gradient with respect to the last D component, it lies in the sigma. So that's how we define the sigma hat here. So we have the E, we have the jet, and then we have the sigma. And so in order to fit that into the theorems, we just have to check that the sigma here is Winnie omega convex with some Winnie constant. It happens to be the same Winnie constant. And we just have to check that the Cook-up data satisfy the hypothesis of the scalar version of the theorem. So once we, so it's equivalent to checking the Winnie conditions. So that's due to the classical Winnie extension theorem. So the moral of the story is that solving the problem for Cm omega on Rn's with the value on Rd is equivalent to solving the problems for Cm plus 1. So it's 1, in terms of regularity, is 1 degree higher. But it's real valued on the domain is Rn plus D. So we are going to upgrade the dimension of the domains by D dimensions. So that's essentially the upshot of this talk. So okay, so I will finish here, and so if you have any questions, I will be happy to answer them.
Any questions? You talked about the refinement stabilizing after L, capital L.
Mm-hmm.
Does that L depend on X?
No, it doesn't depend on X. So the only thing that it depends on here. So this L here is determined a priori by the numbers of derivatives that you look at and then the dimensions you are in. So it's very explicit.
Would it be good
Mhm.
So how is it that this makes no difference to the number of steps that it takes for the scheme to stabilize?
Uh,
I probably misunderstood something.
wait, so
It seems like this refinement scheme here is depends on these neighborhoods, local neighborhoods.
yes.
So how is it that this does not translate into any dependence in the number of steps it takes to stabilize?
So this just a local condition that tells you that the sets should talk to each other in a compatible way. So the compatibility here is actually this case up here is so if you have it's essentially the same as proving the finiteness principle. That so this, if you look at the proof of that, this thing here is independent of this epsilon or this delta here.
But if you have a line and lots of little delta neighborhoods, then somehow talking, it's not the case that for one piece here to talk to another piece here, it has to go through all these neighborhoods, and so it takes longer to stabilize. That is not.
Oh, this is for any epsilon, and so any epsilon, this has to be true.